Okay, a little tough to read. Okay, so suppose that I have a certain concentration of sodium chloride coming into my lake, C, at a certain rate, Q. Right, and I also have some outflows from that lake, Q1, Q2. Right? Now, I'm interested in the concentration of salt in that lake. How would I calculate the concentration of salt in this lake? Using this sort of box model idea. What is the rate of salt flow into this lake? How would you represent that using the variables there? The rate of mass coming in.
Q.
Okay, that is, Q is a flow rate. So that's cubic meters of water per second.
So you do Q times C. That would be the amount of salt.
So if I look at the product of Q and C, Q is in cubic meters per second. C is in, well, it could be milligrams per liter. It could be, let's just say, milligrams per cubic meter here to make it easy. Right? And we have basically mass per time. Right? Mass, grams per time. Right? And of course, you've got to make sure the units are consistent. So I could just multiply Q and C together, and that would tell me the rate of mass coming in. So I will go ahead and write Q in 1, C in 1. That is the rate that mass is coming in. All right, what's the rate of mass going out? You've got two outflows here. Right, so you'd add them together. Q out 1, C out 1 times, Q times C1 plus Q2, C2. Okay, so just writing that out. Q out 1, C out 1. And why did I put plus here? This is the rate that mass is coming in minus the rate at which it goes out. Q out 2, C out 2. Okay?
Also, in your diagram, there's one input and two outputs.
Yes. Okay. Exactly. Okay. So the only thing we need to represent now is the time rate of change of mass inside the system, the rate of accumulation. How would we do that?
Differentiate with respect to time.
Differentiate what with respect to time?
Everything.
What's everything?
All the multiples that we have here.
Well, I want to understand what's inside the system, right?
Right.
So I just want to represent the rate of mass accumulation inside the system. What are the system variables you're given? You're given two variables. One's the volume of water in the lake. The other is the concentration inside the lake. We make an assumption here. When I put a pinch of salt in the lake, boom, it spreads out instantaneously throughout the lake. Call this the instant mixing assumption. It sounds ridiculous, but you wouldn't believe how well it works. A lot of systems, you'd be surprised all around you design this way. So it works well. Over certain time constants, okay, and the types of problems you're dealing with. We're going to make that instant mixing assumption. Okay. So if I multiply the volume times the concentration, remember concentration is mass per volume, right? I've got mass. And if I go to the time derivative of V times C, then I've got the rate of accumulation, mass per time. So I'll just go at V cis, C cis. And that would be it. What's C out equal to if we have an instantaneous mixing?
V out. C out.
V cis and C cis.
Say again?
V system and C system.
The question is, what is C system if we have an instantaneous mixing? right? It means that the concentration of the outflow is going to be the same, right? Because what's coming out comes from inside the system, right? So this, if I can just rub it out here, is going to be C system and C system. 1 and 2 are going to be the same.
Okay.
Now that gives us the ability to do a lot of interesting things. Okay? Because what I can do, for instance, I can pull the volume out. I could assume that we're at steady state. At steady state, all time derivatives go to 0, right? So if I did that, right, this goes to 0. And it would be rather straightforward if we know what Q in is and C in is, right, to calculate the concentration inside the system. Because if we're at steady state, there's no accumulation of volume inside the lake. So Q out, the sum of Q1 and Q2, has to be equal to Q in, right? All right, so I would now just pull C system out and have Q1 plus Q2 and be able to solve relatively directly. Right. So there's a few important ideas here, okay, to get across. Number one, we can say a lot about what's going on inside a system by looking at what's going on at the edges, if you will. Second thing to take away from this is to look at units, right? Problems that otherwise don't look intuitive can turn out to be very simple. Right? And mass is always conserved, just like energy, right? Especially in these types of, we're not talking quantum physics here. We're talking about simple masses. They talk about the rate of mass accumulation being equal to the rate of mass in minus the rate of mass out. Well, if I can simply get to mass per time and then look at the edges of the system, I know exactly what's going on the inside. Right? I can solve some differential equations if I need to, but I may not need to. Right? Maybe I do. Now I can show you, and it's here in the notes, that if you now, instead of talking about the concentration of a pollutant inside of a continuous phase, we talk about salt inside of water. What if I was talking about the continuous phase itself, the water? Has the same units as concentration, right? Mass over volume. We talk about the density of air, the density of water. Density. Mass per volume. How much mass in a certain volume? Water is more dense than air. We can go to a handbook and tell us what the density of water is, right? Gram per cubic centimeter or something like that. Right? And we can basically go through and substitute rho, which would be density, for concentration, and make these same arguments. I can change all these C's to rhos. But what would come out in the end is something very obvious. That if I'm talking about pouring water, or let's say flowing water into a lake, and suppose that I'm putting water into the lake at a fast rate, but I'm not taking any out, what happens to the volume inside the lake? It goes up. If I have equal quantity, like the continuous phase, water, going into that lake, as I have the outflow rate, it's the same. So the volume of the lake is going to remain steady. Right? You ever play this game with a sink? And you got a drain there, right? And you can sort of crank up the faucet at the rate at which water is going in. And you find that point where the water level just stays the same. Right? You know it from experience, right? The mass inside the system is being conserved, of course. So we can calculate those sorts of rates. Right? So when we're talking about continuous phases, you remember the water is conserved. So we know exactly how much is coming in, and we know exactly how much is coming out. Then we know exactly what's happening inside the system. Right? So sort of building some intuition and getting you to think about some Physics 101 things, or high school things even, maybe a different way. Okay? But you'd be surprised what kinds of problems you can, with just these basic ideas, one could begin to address even BOD problems. You can even model paper mill effluent in a lake with just a few more concepts beyond the bathtub equation. Now, you remember what biochemical oxygen demand is. We talked about organic matter decaying facilitated by microbial growth inside of some water system, right? And these microbes, these aerobic microorganisms, are going to consume oxygen, right? And as we can see here on the screen, they're going to make more cells, some microbially stabilized products. They can convert carbon to CO2. Right? Well, this is important to consider. I'm not sure we gave the example. Has anybody been to the Shedd Aquarium before? Just one person? Couple? All right, more than a couple. Okay. So you ever take a look at the fish in there and notice that some are ugly and some are really pretty? And then further correlate that. And it turns out that the sort of desirable fish come from, well-oxygenated systems. And the ugly ones come from, well, the Great Lakes and, lakes and things. And it tends to be that way, that a high, at least 5 milligrams per liter of oxygen is desirable in a system. Otherwise, the oxygen is depleted to a level where it begins to affect the ecosystem. Okay.
And it makes the fish ugly?
Well, I'm exaggerating. It doesn't make them. But the pretty fish need a little bit more oxygen.
Interesting way to think about it.
I'm just oversimplifying as I always do. But, but the point is that desirable things, plants and higher forms of animal life, need lots of oxygen. That's the message. So we want to make sure our systems have enough oxygen. If we're just putting paper mill waste and sewage treatment waste, or the effluent from a sewage treatment plant into a river, well, it's going to have an impact on the oxygen levels in that receiving water. Okay. And what we want to do is quantify that a little bit. But before we talk about the decay reaction, I want to talk about how that stuff goes in there, because it's exactly the same development. For instance, we can, with what we've just discussed, take this example where we've got a paper mill discharging a certain flow rate of treated effluent, because you can't just put the waste directly, and you're always treating it first. But note number one, treated effluent can have environmental impact also, and it costs a lot. Flow rate's 2 cubic meters per second. The biochemical oxygen demand is 50 milligrams per liter, and that's entering a stream, and that stream has a flow rate of its own of 10 cubic meters per second, and its own BOD, a background BOD, of 20 milligrams per liter. So if we assume instantaneous and perfect mixing at the outfall, calculate the BOD 5 in the river just downstream of the outfall. And I'll describe what that little subscript 5 means in just a minute. Okay. Well, we can go back to our trusty equation. The rate of mass accumulation in the system is going to be the rate of mass inputs minus the rate of mass output, and we can calculate this. No problem. So let's do it. Okay. So what is the rate at which mass is entering the river, the BOD mass? You've got two sources, two inputs, right? One is upstream, and one is from the paper mill. And we're looking just downstream of the outfall, right? Two inputs, right? So how would I represent the rate of BOD mass entering the system here?
10 plus 2.
All right, just in terms of letters, you can just we take those numbers and multiply them together, right? So it's the flow rate times the concentration gives us a mass per ton, right? Cubic meter, 1 cubic meter is 1,000 liters. Right? That might be the missing number that some of you are looking for, right? So the rate of mass input, if we just start with the background, is 10 cubic meters per second times the concentration of BOD, which is 20 milligrams per liter, and 1 liter is 1,000 liters in a cubic meter. Okay, so that's a rate from source number 1. From source number 2, we go through the same argument here. Here's upstream. Here's a paper mill. So same sort of argument. We've got 2 cubic meters per second coming in times 50 milligrams per liter, and then our conversion factor, 1,000 liters in a cubic meter. What's the rate of mass leaving the outfall? Well, we're interested in the concentration. What is the flow rate? What we would call Q out here.
12.
It's 12. That's our bathtub equation, right? That's the continuous phase, water, right? 10 plus 2 is 12. There's no other sink there. It can only go downstream, right? That's a continuous phase. So we've got now 12 cubic meters per second times the concentration just downstream. And we solve, and C is equal to 25 milligrams per liter. Now that's useful, because in a few minutes we're going to talk about how this 25 milligrams per liter is going to decay, and then we're going to relate that to how much oxygen is actually consumed in the river. Now before we do that, I want to complicate this slightly and look at a distributed source. All right, we talked about the cryptosporidium outbreak in Milwaukee. We said, well, it had something to do with these distributed sources of pollution. All right, here's a distributed source of BOD. Could be from farmland upstream. Okay. How do I represent that mass flow into the river from a distributed source? Well, generally you got to do a lot of averaging. Okay. And you would represent this as the mass per time input per length. And then you look over the whole length. Right? Or if you're interested about halfway downriver in the middle of this distributed source, then you would only look at half of it. Right? So what we do for distributed systems, we talk about flux, which is sort of a mass per time per unit length. Okay? So let's talk about, forget the point source downstream, because we just did that problem. We're looking at the distributed source upstream. What is the rate of mass coming in for the distributed case? Okay, you're given in the problem here up on the computer, right, that BOD enters the river at 0.1 milligram per liter. That's the concentration, right? But the area flow rate, cubic meter per second per meter, right? Per meter, that's per length, right? And that's how it's represented for the distributed source. Okay. So now, I want to look at the BOD5 upstream. Okay, assuming that over that 8 kilometers that the BOD is conservative. Which, if the flow rate's high enough, it would be. Okay. So how do we get the concentration just upstream of the point source? Right. Well, I can look at how much mass enters over that. It's a 2 kilometer area. It's distributed over 2 kilometers, or 2,000 meters. Okay, that's the non-point source. So if I just multiply, I look over the whole distributed mass, 0.005 cubic meters per second flow rate times 20 milligrams per liter times Yeah, I'm sorry, 20, times 2,000 meters. Sorry, forgot my other meter here. Right? Times 1,000 liters is a cubic meter. All right, that's how much mass has come into the system, right? Mass per time from that source, right? And it's the only inflow. So we assume upstream of the distributed source that there is no BOD. It's clean. I can represent this in a different way that some of you might be familiar with as an integral. Right, from the beginning of the distributed source to some distance, x, inside the distributed source, I take my area source rate. I'm going to write it as words here. Times the area source concentration. Right? And abbreviate concentration, dx. Right? Sorry. I saw some perplexed looks. Okay, it's cubic meter. Right? The area source rate, the area source concentration. Right? And if I integrate this, these are not functions of x. They're constant. Right? So all that happens is equal to what we got into beginning last Friday, and we'll finish up today, is a discussion of what happens to oxygen-demanding wastes when you put them into a closed system, of course, assuming that there's some oxygen there to be consumed. We went through a little bit of the mathematical development. We looked at first-order reaction kinetics, how this oxygen-depleting waste decays over time, and we basically came up with an exponential function to describe that. And what we need to pick up with, especially to help you for homework number 2, is what happens when we put these oxygen-demanding wastes into a river. There are a few factors that will influence the concentrations of dissolved oxygen inside the river. The first is the rate at which the oxygen decays. Okay, the oxygen-demanding waste decays over time. That will reduce the amount of oxygen in the river, which is, of course, a parameter we're interested in. Over time, also, through contact with oxygen in the air, that river will become re-aerated. So that is a second mechanism. And obviously, they're moving in opposite directions. Deoxygenation, reducing the amount of oxygen in the river, and, of course, re-aeration, increasing it. Okay, so we're going to model those two phenomena. We're going to solve a differential equation, write it up on the board for you, take a look at the characteristics of the solution, extend it just a wee bit further, and then talk about homework 2. Before we get going, and I shut the door over here, are there any questions? Grim.
Aeration of the river. Like considering a river that has no levels of pollution whatsoever, the oxygen level doesn't keep building up, right?
There's a maximum amount we're going to talk about.
So, in some sense, like the amount of re-aeration is itself dependent on the amount of oxygen that's already in there.
You got it. And we're actually going to talk about that in just a couple minutes. Yeah, we say that the rate of re-aeration is proportional to the amount of deficit there. So if there's a lot of, and that comes directly from physics, right? Laws of diffusion, concentration gradient. Right? If you have a big gradient, then it will diffuse in quicker. We'll come back to that point. Other questions? Administrative questions? Okay. So up here on the screen, we've got basically today's agenda on the computer here. Should show up, definitely. Okay. Biochemical oxygen demand modeling. We're going to finish that up. Talk about how to model it in the river. That's where we're going. Talk about homework 2. And then we'll get into session 7 proper. And in session 7, we're going to introduce you to the concept of LCA, which is something we're going to keep coming back to over and over again, life cycle assessment, and the use of such data as the basis for eco-design and manufacturing decisions. To keep it interesting, because LCA can be a dry subject on its own, we're going to present LCA thinking in the context of an example. We'll talk about the automobile. Okay, so we should get through a healthy amount of that session today and be all caught up by Wednesday. As a reminder, there's no in-class sessions next week. I'll be in Berlin, and I'll let you know how to contact me on Wednesday while I'm over there. Okay. Taking it to the board now, we have to model these two phenomena, reaeration and deoxygenation. So the deoxygenation rate, we said, is going to be proportional to the amount of oxygen-demanding waste that's in the system. Okay? So we're just going to define a constant of proportionality, Kd, and I can put an equal sign here, times L of T being the concentration of oxygen-demanding waste. How do we describe the deoxygenation rate mathematically? I'll come back to that in just a second. Okay. For the reaeration rate, as was just suggested, right, this amount of oxygen inside of the system cannot increase to infinity, right? So we're going to say that the rate of reaeration is proportional to the amount of dissolved oxygen deficit in the system. We're going to define deficit as D. Okay, so here's Ka. This is our proportionality constant for reaeration. And D is going to be the dissolved oxygen deficit. And what we mean by D, if I can just write another equation, dissolved oxygen deficit in milligrams per liter is equal to the saturated amount of dissolved oxygen. That's the maximum amount of dissolved oxygen that the water can hold, right? Minus the observed dissolved oxygen concentration. And you might think it's a little bit strange that we're talking about dissolved oxygen deficit instead of dissolved oxygen. Remember, dissolved oxygen is that parameter that we're actually concerned about. Right? We're going to talk about deficit instead because it makes the equations a little bit easier. Okay, but it's very simple. This is a constant. Now, we said cold water can hold more oxygen than warm water. Cold water, such as the Big River in the Northwest Territories of Canada, might have a dissolved oxygen saturated level of 13 milligrams per liter. Whereas summertime in these parts, it might only be something like 8 or 9 or 10. Okay. So we're talking about dissolved oxygen deficit. Now, how can we express the change in dissolved oxygen deficit per time? Right? Well, that's just simply dd dt. Okay? So I'm going to write it dd dt because that's really what we're interested in, right? It's how that deficit's changing as a function of time. We know that there's a rate of deoxygenation. We know there's a rate of reaeration. If we're only modeling these two sources of contribution to the deficit, then the time rate of change of deficit is just going to be a combination of these two terms. So we can talk about this as being the deficit increases when deoxygenation increases. So we're going to put Kd L of T here. The deficit decreases when there is reaeration. So we're going to subtract Ka times D. It's a different question.
Revised notes for this section here. For deoxygenation rate, you say d dt equals Kd Lt, and for reaeration rate, you say d dt equals negative Kad. And then you also say that d dt equals the combination of the two.
Negative Kad, right?
Well, you just say that d dt equals three different things.
Let's come back to the question.
Okay.
Because I don't actually have the copy you have in front of you.
Okay.
It could be a typo or it could be a misunderstanding. So, or they both could be right. But let's review it later.
Okay.
What I do know for sure is that, and it seems to be consistent with the first part of what you said for sure, is that the deoxygenation increases the deficit and the reaeration decreases the deficit. Right? I mean, we could have put the negative here if we wanted, right? Yeah, that doesn't matter. Okay, but the key is to understand the combination. Now, it's an ordinary differential equation. You need one boundary condition to solve it, and our boundary condition is at t equals 0. We're just going to say d equals d naught. And that's all we need to go. And we can solve the equation. You can look it up in a handbook just as well. But if you're wondering where this equation came from, we talked about it on Friday, right? Just like the checking account. The rate of mass accumulation is equal to the rate of mass in minus the rate of mass out. Okay, we flipped it around to talk about deficits, but it's the same idea. Right? Mass conservation is all it is. And if you solve this equation, the answer, Kd L naught over Ka minus Kd times exponential minus Kdt minus e to the minus Kat plus d naught e to the minus Kat. That's it. Two terms. Time equals 0, d equals d naught. This is the contribution of reaeration, contribution of deoxygenation. Now, for a river, we can think of time as being distance. So the river is going to have an assumed flow rate, which is constant. Right? So we have the time is equal to the distance over the velocity of the river. Right? So for a river, t equals the distance x minus u. And we could substitute x over u in for all the t's and solve this as a function of distance. Right? The t's disappear. U would be given to you as a velocity, and suddenly you have the dissolved oxygen deficit as a function of position. Okay, and that's important. And as we take a look here on the screen, and let me see if I can, if I've got my hyperlink working. Yes, I do. There's our equation, and it'd be a little hard to read on the TV here. But the characteristic sag curve is what's shown as a function of distance downriver. What does this mean? If I put my paper mill waste into the river, the dissolved oxygen right in front of my property may not be very well affected. Yet downstream, at some critical distance, that dissolved oxygen will be at a minimum. All right? Suppose there's a resort downriver or something like that. Right? We may be affecting them much more than we're affecting ourselves, because it takes time for that deoxygenation to occur. Okay? So we call this the Streeter-Phelps oxygen sag curve. And it is described completely by this function d. Right? And it's also shown here on the screen. Okay. So we're pretty much almost there. Okay? Because we can superimpose multiple paper mills and sewage treatment plants on top of this. It's just accounting. Question?
Lost in the flow?
Yeah, u is the flow rate. Yes, so the velocity. So the volumetric flow rate. If we assume that the area is constant for the river and divide by the area, then you get the speed of the river. And I'll show you what that is in the big river example. Okay. But there's only one more thing that we need. And that is to consider the fact that when paper mill waste enters a river, especially a slow-moving river such as the big river. In fact, this is a Northwest Territories of Canada, where the BOD, or let's call it the dissolved oxygen concentrations in the river, tend to be their lowest during the winter. The river is flowing especially slow. It may only move about 1 kilometer a day. So what happens at paper mill waste? Is it going to stay suspended, or is a good fraction of it going to fall to the bottom? So there's actually two sources of loss here in the system. There's microorganisms degrading that paper mill waste, consuming oxygen in the process. There's also settling to the bottom of the river, forming a blanket, if you will, on the river bottom. So 2 contributions. We talked about the decay of oxygen-demanding wastes only being a function of the microorganisms on Friday. So we need to modify that slightly to consider settling also. Okay, so essentially the rate of disappearance of that oxygen-demanding waste can be higher than we would predict just looking at the microorganisms themselves. It may be, in fact, driven by settling, depending on the situation. That's number 1 change. So there's a KD in here that's going to become a KR. One of them is going to become KR instead of KD. The other thing that we need to consider is that the microorganisms, we call this benthic respiration, at the sediments themselves may suck up some of the oxygen from the river. And we need to account for that term also. So if we look here at our equation, the deficit change as a function of time being a function of deoxygenation due to suspended microorganisms minus reaeration, we're going to have to add one more term for deficit that comes from the sediments themselves. Okay, so 2 very minor changes. And they won't affect the form of our oxygen sag curve. So let's just go through that. Okay, and the first thing we need to do is modify our equation for L of t. Remember, we modeled dL dt. This is the change in concentration of the oxygen-demanding waste as a first-order kinetic equation equals the Kd L of t. So faster decay rate when you have more of it, right? It tends to be like my kitchen. If there's more food in my kitchen, it tends to disappear more quickly. If you've got a little bit of food in the kitchen, you're going to conserve it for a longer time, right? You remember the blackout last month. I'm sure we all experienced that. Well, we're going to consider settling now also, and we're going to consider settling as a first-order equation also. So essentially, what we can say is Kd L of t plus Ks L of t. So the settling rate is, the change of oxygen-demanding waste as a function of time due to settling is also proportional to how much is there. That makes sense. You got a big glob of it, it's going to fall faster. Okay, and I'll rearrange a little bit. Equals Kd plus Ks times L of t. And then I'm just going to call Kd plus Ks equal to Kr. So Kr is the rate of loss of oxygen-demanding waste. But the form of the equation in the end is exactly the same. Kr L of t. And so is the solution. So L of t equals L naught e to the minus KRT. So a slight change there instead of KDT. So you can think about it originally as we treated the settling is equal to 0 in our development from Friday. I didn't want to complicate the presentation by talking about settling last Friday, but an easy modification. And we said there's one more. We have to account for settling in our deficit equation, right? Capital D, dt, right? So let us model the sediment oxygen demand, SOD, as a 0-order equation, even simpler, but it works. Okay, so we've got Kd L of t minus Ka times capital D plus S, where S is the sediment oxygen demand. What are the units of S? What are the units of D? Well, from back here on panel 1, D equals the saturated dissolved oxygen concentration minus the dissolved oxygen concentration in the river, right? So it has to have the same units. D is in milligrams per liter, right? So dt is milligrams per liter per second. And it doesn't depend on anything. It's just a constant. And that might sound a little bit weird to you, but the modeling works. And we don't need to make it more complicated if it works. And this has been proven out up in northwest Canada for this situation. We could complicate S if we wanted, but there's no reason here. But we need it, or else our model doesn't do as well as it otherwise would. Okay, so sediment oxygen demand. Okay, so our equation does change. Our sag curve as a function of distance changes. Essentially, we add a term for sediment oxygen demand. So the form of the equation, D equals L naught KD over KA minus KR times E to the minus KRT minus E to the minus KAT plus our sediment oxygen demand term, S over Ka, 1 minus E to the minus KAT, plus D naught E to the minus KAT. We see our original solution is unaffected by the sediment oxygen demand, except we add a term. Question?
Does Q equal D?
I don't see a Q anywhere in this development.
dq dt equals k.
Oh, this is a D?
Oh, that's a D?
Sorry?
Oh, okay.
I'm still getting used to the chalkboard here.
Sorry.
Not bad?
No.
Doing my best. Get used to writing on the Palm Pilot, and then nobody can read your writing anymore. Other questions? Okay. Well, this is it. This is as far as we need to go. Now the rest is just bookkeeping. Okay, and we can take it to the slides here. And this could be a little tough to see on the inside here. But basic idea here, you've got the equations the same. As the screen comes down here, we'll make it a little bit easier for the folks in class to see. Perfect. Okay, so we've got our Streeter-Phelps equation with sediment oxygen demand, just as we've written down. The question is, how do we apply it to the big river? Illustrated here. All right, that's our question. How do we apply this equation to the big river? We're going to use a concept well known to those of you who've been exposed to the idea of finite element analysis, right? Except this is nowhere near as complicated. What we're going to do is we're just going to chop this river up into pieces. It's about 1,000 kilometers in real life. We're going to break it up into about 50 segments. And we're going to handle each of those segments as a row in an Excel spreadsheet. Okay? And so how we do that in just a sec. Okay? But we're breaking this river up. And we're doing this in logical places. For instance, where there is a paper mill, we'll make a reach. Where a tributary inflows to the river, there'll be another reach. Just breaking up, chopping it down. And if it's a really long reach, then we'll break that one into two just for convenience and better accuracy. Okay. So the first concept in applying this Streeter-Phelps equation with sediment oxygen demand to the big river is to recognize we break the big river up. And here it is, the real problem, modeled again after the Athabasca. You've got 5 industrial facilities. These are the paper mills. 4 sewage treatment plants, all of which contribute BOD, oxygen-demanding wastes, to the river. And tributaries that are all inflows. None of these are outflows. So from beginning to end, from left to right, as the river flows from left to right, the volumetric flow rate continues to increase. Okay. And, okay, so we're basically breaking this up into 52 reaches for the big river. And then there's River 4, which is a rather large river that feeds into the big river. Okay, this is actually the Lesser Slave River, and there is a paper mill on this river. Okay. So we model 4 reaches for, we call this river 4 in the problem. All right, so first concept, breaking this up into segments. Okay. There's our equation up at the top. What do? For each segment, we're assuming that the sediment oxygen demand, the dissolved oxygen deficit, the flow rate, and the amount or the concentration of oxygen-demanding waste is constant. Right? Just like finite element analysis. We're assuming in each segment that it's constant. So what do? Well, you know the old saying, I think we've used it before in this class, dilution is the solution to pollution. Right? So suppose that I have a concentration of oxygen-demanding waste, L. And I've got an inflow. And I'm going to assume that inflow has no oxygen-demanding waste in it. Right? So it's clean water, essentially, coming in. What happens is this L of j at the beginning of the reach is going to be somewhat less than L of j minus 1. So the thinking here is, okay, take the previous segment, account for any inflows, and in this problem there's only inflows, calculate the concentrations of dissolved oxygen deficit and oxygen-demanding wastes, get L naught and D naught for our equation, right at the beginning, and then calculate it for the end. Right, so L of j minus 1 is defined at the end of segment j minus 1, and L of j is at the end of segment j. But you know from the Streeter-Phelps equation here that you need L naught and D naught, and that these are in turn affected by any inflows, if they're there. So we modify L naught for j by the inflow. Okay? And you know how to do this because we gave this introduction to systems analysis on Friday. Just to refresh your memory, right? The rate of mass in has to be the rate of mass out if there's no accumulation in the system. And we're saying there are no accumulation sources in the system. Right? We're looking at a point. What comes in must come out. Okay, so this is the concentration, right? The mass rate on the inside as it is affected by upstream and the inflow. Right? Remember the 2 examples we did on Friday. It was exactly the same problem. So, L of j minus 1, Q of j minus 1. And we've represented here little q, that's the rate of inflow. But really little q, that's our continuous phase, right? That's the flow rate, that's the water. So we know that little q of j equals capital Q of j minus capital Q of j minus 1. Okay, so these are all parameters you have except for L of j. And that's what we want. That's L naught here. Right? And we're going to use it. Really, this probably should be L naught of j, just to avoid confusion. Okay, but we're calculating L of j at the end using the Streeter-Phelps equation. Okay, so you get L of naught for that reach. And that's what this equation gives us. Okay? So we can solve it. Right? And there's L naught of j for that reach. I have corrected it here. Okay? A function of all the things you know, which is fantastic. And in fact, you can do the same thing for D naught. D naught's a mass. I mean, it's a deficit, so people in the past have gotten confused by it. So how do you keep track of mass deficit? But it's the same thing, and it's related by an equation we know. We're really talking about mass here. So the thinking in terms of deficits is the same thinking that you would have for dissolved oxygen itself. Right? The oxygen is conserved. The dissolved oxygen saturated level is fixed, right? And therefore the deficit's conserved too, right? Don't you wish you could just make the deficit go away? But you could give a similar development for D naught of j, which is what you need to calculate D of j at the end of the reach and L of j at the end of the reach. Q of j is known if you know the inflow, and S of j is constant throughout the problem. Right? This doesn't sound so hard at all. Okay, so I can substitute in to the Streeter-Phelps equation with our bookkeeping parameters. And it looks like it's getting a little bit hairy. But what you would do in a spreadsheet, and what has been done for you already, is to define these terms, right? This is the initial L naught of j for the reach, L naught of j. So you just put a column in the spreadsheet for L naught of J. To convert that to dissolved oxygen deficit at the end of the reach, we've got this factor over here, which we call H. This is the conversion of biochemical oxygen demand to dissolved oxygen deficit in the river. It's a function of time, but really, as we said, it's distance over velocity, both of which are known parameters, so we know T here. Same here. B sub j, is the within reach SOD factor, converting SOD to a deficit at the end of the reach. Here's our D naught of J, our initial dissolved oxygen deficit for the reach, and then its conversion to dissolved oxygen deficit at the end of the reach. All columns on a spreadsheet. I'll show you the implementation in just a minute. So that's for one paper mill. All we need to do is use the concept of superposition to look at those contributions to dissolved oxygen deficit from each paper mill. And we're talking about plug flow here, so no downriver paper mills are going to affect the concentration upstream, right? Only downstream. So we have to place, in terms of our spreadsheet, in the correct locations, the treatment facilities and the paper mills. Okay. So this is where it's coming from, and we're going to ask you to understand these basic ideas, okay? But we're not asking you, as we have in semesters past, to actually develop the model. As I mentioned before, you can get lost developing the model. You know, you could be looking for a little minus sign in terms of the development, lose a day doing that, where you could be really thinking about the most important issues, which are the underlying concepts, the systems concepts, and how we can use this type of modeling for policy development, right, and eco-design. Okay? So multiple BOD sources brings us to homework 2. All right, this is a big river. I think we've said everything that's on this slide already. It's 1,080 kilometers. The flow steadily increases because we have influx from tributaries and other rivers. Break it down into 52 reaches, corresponding to facilities and tributaries, rivers, and sewage treatment plants.